We have seen definition and examples of exact differential equation. Now, we want to see how to decide whether a given differential equation is exact or not. That means we want to determine some necessary and sufficient condition for a differential equation to be exact. In this presentation, both the condition and its proof are discussed. Before stating directly the condition, let me recall the definition of exact differential equation. The differential equation in the form m dx plus n dy equal to 0, where m and n are functions of x and y, if there exists a function f of xy equal to c such that its partial derivative with respect to x, that is dabba f by dabba x, is m, which is coefficient of dx in the differential equation, and partial derivative of f with respect to y is n, which is coefficient of dy in the differential equation. If such a function exists, we call the differential equation as exact differential equation. Further, we know that since m is dabba f by dabba x and n is dabba f by dabba y, this complete LHS is nothing but total derivative of that function f. And our differential equation becomes derivative of function f is equal to 0. So obviously the solution is f is equal to c. So that function itself is the solution of that differential equation, which is exact differential equation. Let us recall one example. Consider the simple differential equation y dx plus x dy equal to 0. Since m and n are very simple, just by observation we can say that for the function f is equal to xy, dabba f by dabba x is y and dabba f by dabba y is x, and which are coefficients of dx and dy, that is they are our m and n. Hence, by definition, the differential equation is exact and xy equal to c is its solution. But it is very hard to determine whether such function exists or not. It is an unknown function and our definition depends on that existence of unknown function. So we want to find some condition which depends on these two functions m and n so that we can verify it whether it is exact or not. Okay, so for determining that, let us start with our given differential equation is an exact differential equation. Since it is an exact differential equation, we know that there exists f such that dabba f by dabba x is m and dabba f by dabba y is n. We don't know that f, but we know that existence of f is there. F exists, at least we know that. If we want to determine some condition on m and n, what happens if we take derivatives of m and n? These derivatives, partial derivatives of m and n, are nothing but second order derivatives of f. And we know one theorem, that is mixed partial derivative theorem, which states that this mixed partial derivative of f, that is dabba y, dabba x, is same as dabba 2f, dabba x, dabba y. That means order is not important. Obviously some condition should be there on f, but then by mixed partial derivative theorem, these two partial derivatives are always equal. But what is this dabba 2f by dabba y, dabba x? That is nothing but dabba by dabba y of dabba f by dabba x, but dabba f by dabba x is m. So this partial derivative is dabba m by dabba y, and the second partial derivative is dabba by dabba x of dabba f by dabba y, that means it is dabba m by dabba x. That means if our differential equation is exact, because of this mixed partial derivative theorem and existence of this function f, these two partial derivatives dabba m by dabba y and dabba m by dabba x must be equal. That means this is a necessary condition, but surprisingly it is sufficient also. So the necessary and sufficient condition for a differential equation to be exact is dabba n by dabba y is equal to dabba n by dabba x, and that condition depends on our m and n. So for given differential equation, we can calculate these two partial derivatives. If they are equal, our differential equation is exact. Let us check this condition with our previous example. Our differential equation is y dx plus x dy equal to 0. Here m is y, n is x, and then dabba n by dabba y is 1, which is same as dabba n by dabba x, and we know that already that differential equation is exact. Now let us prove this. So before that, we state it in the form of theorem that a differential equation m dx plus n dy equal to 0 is exact if and only if dabba n by dabba y is equal to dabba n by dabba x. This is equation 2, this is equation 1. We prove first necessary part. Necessary part means the condition is necessary to be exact. That means whenever the differential equation is exact, it must be true. So here we are assuming that differential equation 1 is exact, and we are going to prove that this is true. In fact, by determining that condition, we have proved it already, but in proper way, we have to write it as follows. Suppose the differential equation 1 is exact, that means there exists a function f such that dabba f by dabba x is m, dabba f by dabba y is n. So dabba n by dabba y is nothing but dabba 2f by dabba y dabba x, and dabba n by dabba x is equal to dabba 2f by dabba x dabba y. We assume that our function f is continuous and its partial derivatives are also continuous, and it's okay because it is a solution of that differential equation. Then by mixed partial derivative theorem, these two derivatives are equal. Since they are equal, dabba n by dabba y and dabba n by dabba x are also equal, and that is the proof of necessary part. The proof of sufficient part is not that much obvious, but one interesting fact is this proof helps us in constructing the solution of exact differential equation. In that sense, it is a constructive proof. Okay, so let us start with that. For the given differential equation 1, that is m dx plus n dy equal to 0, the second equation, that is condition dabba n by dabba y equal to dabba n by dabba x is true. That means we are assuming that this condition is true, and we are going to show that the differential equation is exact. To show the differential equation is exact, we have only definition. That means we have to provide one function f such that dabba f by dabba x is m and dabba f by dabba y is n. So we have to construct that function f satisfying these two constraints, that dabba f by dabba x should be m and dabba f by dabba y should be n. And while constructing that function, we use somewhere this condition. That is the idea of the proof. Okay. So we have to find that function satisfying these two constraints. Now we know what is m and which is partial derivative of our function, of our required function f. So obviously, if I integrate this m with respect to x, I should get f. Not exactly, but some part of it. That means we should integrate that fx first with respect to x. Fx means m. But is it that same function f? Okay, let me explain this procedure with one example. For example, consider that for some unknown function f, its partial derivative with respect to x is 3x square y. That means I want to determine f such that fx is equal to 3x square y. Obviously, f must contain the term x cube y, because partial derivative of x cube y is 3x square y, and that is integration of 3x square y with respect to x. But since we are integrating it, we add constant of integration, that is c, because if I differentiate this, I get my original function back because derivative of c is 0. But here the fact is, I am not differentiating it in general, but I am differentiating it partially with respect to x. So, if I add instead of c any function of y, then derivative of that function of y with respect to x is 0 always. For example, instead of c, consider say y square. What happens if I add y square here? What is its partial derivative with respect to x? It is 0. So, partial derivative with respect to x of x cube y plus y square is still 3x square y. So, this can be my f also. And why only y square? C can be any function of y. That's why if one partial derivative is known to us, we can say that the function is nothing but integration of that partial derivative with respect to x plus any function of y. And this is the basic idea of our proof. Since we know the partial derivative since we know the partial derivative fx as m, we are going to write our function as f is equal to integration of m dx plus any function of y which we don't know. That denote this by equation 3. So I can calculate this term now because m is known to me, but I don't know what is g of y. But to find that g of y, we are going to use the another constraint. The another constraint is dabba f by dabba y should be n. So differentiate this with respect to y. So what is dabba f by dabba y? It is dabba by dabba y of this term integration of m dx plus g dash of y. Because it is a function of single variable, it is ordinary derivative, that is g dash of y. We want to find our f such that dabba f by dabba y is n. And therefore, since dabba f by dabba y is n, we equate it with n, we get n is equal to this. So, unknown thing here is g dash y, because we know n, we know m, so we can integrate it with respect to x, we can differentiate it further with respect to y. The unknown term is g dash y. So, I can write that g dash of y should be n minus dabba by dabba y of this integration m dx. That is, denote this by equation 4. Now, the LHS of this equation is function of y. What is RHS? Here n is function of x and y, m is function of x and y. So, RHS can be function of x and y. So, since we want to determine g of y, g dash of y must be function of y. So, we have to prove that RHS of this equation 4 is function of y only. If it is that, we can integrate it to find g of y and then we can construct our f. So, we have to show that this term n minus dabba by dabba y of integration m dx is function of y only. How to show that some function of two variables is function of only one variable only? Obviously, the partial derivative of that function with respect to that variable should be 0. That means if it is function of y only, that means no x is there. To show that no x is there, differentiate this with respect to x and show that it is 0. If partial derivative of this term with respect to x is 0, that means this term is independent of x. It is function of y only. So, let us calculate partial derivative of RHS of 4 with respect to x. So, it is dabba n by dabba x minus dabba 2 by dabba x dabba y of this integration of m dx. Since by mixed partial derivative theorem, I change the order of this second order derivative and I am writing this as dabba 2 dabba y dabba x of this integration of m dx. That means it is dabba by dabba y of dabba by dabba x of integration of m dx. Now concentrate on this term in the bracket. Here m is there. I am integrating it first with respect to x and I am differentiating that again with respect to x. So these two operations will get cancelled and it is just m. So it is dabba n by dabba x minus dabba m by dabba y, because this bracketed term is nothing but m. And what is this? It is 0 because our differential equation satisfies that condition dabba n by dabba y is equal to dabba n by dabba x. It is 0, that means that term is independent of x, it is function of y only. So I can calculate g dash of y, then I can calculate g of y. Putting that value, I can calculate f of xy. This is the construction of that function. Since such a function exists, we can say that differential equation 1 is exact. So now we know the condition, and that's using that condition we can determine whether a given differential equation is exact or not. So in the exercise, some differential equations are given to you. Using the condition, determine whether they are exact or not. Remember one thing, that compare the given differential equation with standard form m dx plus n dy equal to 0. Identify m and n. Find their partial derivatives dabba n by dabba y and dabba n by dabba x. If they are equal, your differential equation is exact. Try to solve them if they are exact by the procedure discussed in the proof of sufficient part. Try it first. Otherwise, in the next video, we are going to solve some problems which are some differential equations which are exact differential equations, and we are going to solve them by using the method which we have already discussed in the proof of sufficient part of this proof of necessary and sufficient condition. Okay? If you like the video, subscribe the channel Jidnyasa Akadami so that you can get the notifications of more such videos. Thank you.